See you later. Enjoy.
Yeah. Bye. Right. So the reason that I am doing this one is that towards the end of the year, we are going to do a revision quiz on Google Classrooms that covers the whole of P2, so everything in P2. This is the topic that you would have done right at the beginning. You'd have done it still in school, and it was a very long time ago. So I'm going to go through it quickly to remind you of some of the key points. And what we're going to look at is vectors and scalars and forces, and in particular, resultant forces, to help you remember those things. There are two questions up there for you to have a little look at. One of them is, how many parts of the electromagnetic spectrum can you name? And can you give an example of a use for each? Now, if you're looking at that and thinking, I can't do that at all, that's something you need to revise over the next couple of weeks. These are nice, easy things to revise, and you can do the retrieval practice technique that was in assembly. So you can write out the electromagnetic spectrum, you put visible light in the middle, then you put infrared, then you put X-rays, then you put ultraviolet, then you put X-rays and gamma rays, and then you put microwaves and radio waves, and remember those in that order. And you just write it out over and over again until you can remember it. And then for each one, you can write an example of what they're used for. Most of them are quite easy, but there are a few where people get caught out. So microwaves, we need to not just talk about microwave cookers. We need to think about things like mobile phones as well. Okay, so that's just a little bit of revision from the last couple of webinars. So what you need to know, this is another thing that's great for retrieval practice. This is great for making a flashcard and just writing it down. So you need to know what the difference is between a vector measurement and a scalar measurement. Sounds ridiculous, but there's just one difference. Scalars have a magnitude, that means a size. So for example, my mass in kilograms has a size. I could be 10 kilograms or 20 kilograms or 30, but it's just got a magnitude, a size. But vectors have got a size and a direction. So for example, speed has just got a size, a magnitude, 30 miles an hour, 40 miles an hour. But velocity, which says that it's 30 miles an hour north or 30 miles an hour to the left, has got a size and a direction, a magnitude. Remember, magnitude means size, a magnitude and a direction. Okay, so a vector quantity has got a size and a direction. And we can tell that from diagrams. If they give you a diagram in your exam and say, is this a vector or a scalar quantity? You don't need to sit there and think, oh my goodness, I can't remember. If they put an arrow on it, it's generally got a direction. Not always, but generally got a direction. And that's a really, really helpful way to find out. So if you're not sure, look for an arrow. It's got an arrow, it's probably a vector. So here's an example, acceleration. Acceleration is a vector. The length of the arrow is the magnitude. So if we draw a bigger arrow, we say more acceleration. And the direction points in the direction of the acceleration. Things accelerate forwards, or they accelerate backwards if you're reversing. Or if they're slowing down, the acceleration is backwards as well. You'd have an arrow going backwards because it was slowing down. So that really helps us, this arrow idea. So we could even put some numbers on it. So which one has got greater acceleration? How can you tell from the vector? If you had this as an exam question, you would write the bottom one, because the arrow is longer, or because the vector is longer. It's nice and simple like that. The bigger the arrow, the bigger the magnitude, size. So the arrow tells us quite a lot. That's really handy. Both planes have a mass, but mass doesn't have a direction. Mass means how much of something you've got, and it doesn't matter where it's going, that amount that you've got doesn't change. So mass is a scalar. It's got no direction whatsoever. So we've got no arrow. We can't put an arrow for mass. Okay, and there it is. So we could have 690 kilograms, we could have 950. They're different. One's got a greater mass. There's no direction on there because it hasn't got one. So we don't put an arrow on it. So we could put numbers on it as well. So this is what I was talking about before. If we draw an arrow that is exactly twice the length of the other one, that means it's double the acceleration. So here in your exam, if they gave you this plane and said it's accelerating at 16 meters per second, but they hadn't given you an arrow on the bottom one, and they said it's accelerating at 32, draw an arrow to represent that. What you would need to do is measure the top arrow and draw the bottom one at exactly twice the length, because 16 is half of 32. So the acceleration is twice as much here. So the arrow has to be twice as much. And if you look at these arrows, this one is exactly twice as long as the one above. Very important. They are actually drawn to scale in your exam. Okay, so they have numbers, normally have numbers written next to them, and the size is proportional. It means they are drawn to scale. It matters, okay, what length they are. Double the length is double the magnitude, the size, okay? So let's just have a little, so here's an example of, and here, this is here so that you can use it for that retrieval practice business. This is a nice table to learn, okay? Scalar quantities, distance, 20 meters, doesn't matter which direction, 20 meters is 20 meters, whether it's straight up, straight down, left, right, it's the same. Same is true of all of these things. These ones all have a direction. These are the ones, we couldn't draw an arrow. If we were putting temperature on a beaker, we couldn't draw an arrow to show where that temperature was. That's not possible. But all forces, or if we were looking at velocity, and we're going to talk about displacement in a minute, we could put arrows on it. And so that means that they are vector quantities. Okay, so I've got, I have got a quick poll that I'm going to put up here, if I can find it. So there we go. Oh, now, before we move on to look at forces, is that the right one? Let's, oh no, it's not, there we go. So quick poll. Is speed a vector or a scalar quantity? So can you remember that from the last couple of slides? Fantastic. And it's a scalar quantity. Got that completely correct. Brilliant. Okay, so paying lots of attention there. It's a scalar quantity. And that's the sort of question you need to be able to answer in the exam. So if you can already do that now, that's brilliant. But you need to keep reminding yourself, otherwise it will slip away from your brain. Okay. Now, we need to be able to define and say the difference between these four words. And some of them are quite easy. So we probably already know what distance is. Distance is quite simply how long or how far something is in meters. Really easy. Speed is quite easy as well. It's how quickly is it going, normally measured in meters per second in science, or miles per hour if you're driving. Lovely. Nice, easy ones. They're both scalar quantities. They just have a magnitude. Okay, they don't have a direction, but these two do have directions, and they are very closely related. Velocity is the easy one, because velocity is just speed with a direction. So 30 miles an hour up Ditchling Road, 30 miles an hour down Ditchling Road, 30 meters per second to the right. As soon as you put a direction on it, it stops being speed, starts being velocity. Nice and simple. Displacement is a little bit more difficult. So I'm going to use an example to define that one later. But one of the things I want you to do with these slides when they're shared in your classroom is to write the definitions or the difference between these underneath here, because the act of writing it down will help you remember it, and it'll also give you something you can come back to and revise later on. Because remember, we're going to give you a little quiz on this right at the end of the year. Again, this isn't a quiz to catch you out. It's not for predicted grades. It's not going to college. It's not going to be used for anything. It's just for you to have a look and think, am I able to remember these things when I do some revision? If I just read through these slides, try and remember it, am I able to do that? How good is my revision technique? It's not going to be horrible, but it'll allow you to test yourself on that. It's just going to be a Google form. You fill in mostly multiple choice answers. So this one lets me explain. There are some questions on here for you to work out. So a slide I gave you a couple of weeks ago had all of the units on it for physics that you need. So what you need to do is look up these units and find out what that means that they are. So we've got a speed there, we've got a mass, we've got charge, we've got a force, and we've got a velocity. You might remember that. And so all you've got to do is put after each one a V or an S. Is it a velocity? Is it a vector or a scalar? Just put a V or an S after it, velocity or scalar. Now, let's have a look at this idea of displacement as opposed to distance. Okay, so here we've got a skier. And we're going to work out the distance the skier traveled first. That's nice and easy. So they started here. Here they are at point A, and they went along to point B. To get there, they did 40 meters, 100 meters, and 40 meters. So that means that they covered 180 meters from A to B. But then they turned around and they went this way. Here they are from B to C, and they went 40 and then 100. So they've done 180. Now it's 220 because it's another 40. Now it's 320 because they've got to that point. So far, my skier has gone from A to B to C, and they've gone 320 meters. Then they turn around and they go over here to D. So they've gone across, back, and across. And they've gone 320 meters into, sorry, 420 meters in total. 40, 140, so 180. Back this way with another 140, so 320, and then another 100 to there, 420 meters. That is the distance the skier traveled. Displacement is how far are they away from where they started. So they're not 420 meters away from where they started. They started here and they finished here. So they're only 140 meters away from where they started because they went backwards and forwards. Their displacement is how far they are from where they started. And it's also a vector because they are 140 meters to the right of where they started. And it's really important because if they were the other way, their displacement would be 140 meters to the left of where they started. So distance, you add up all of the distances that the person or the thing traveled, but displacement, you just work out how far away they are from where they began and in what direction. It's quite important. Okay, so that's the difference between distance and displacement. So really quickly, let's have a look at some forces now. So with forces, there's a couple of things we need to remember. So one of the things we need to remember is what the units for force are. So let's just see, can we remember the units of force? Anyone go for that one? Anyone remember the units of force? I'm going to put some of those up there. So we've got meters per second, kilograms, newtons. Fantastic. And newtons it is. Sir Isaac Newton, named after him. And absolutely brilliant. So we can remember that. So that capital N there means newtons. And when we're talking about forces, we're always talking about newtons. So here's some more things on vectors and scalars. Again, just putting the a V or an S afterwards. Really important you're able to identify those. So as we just said, a force can be described as a push or a pull. A push or a pull. It can change the shape of an object. So if we squish it, okay, or we can make it move if it's not moving, or we can accelerate it or stop it. So it changes its state of rest or motion. It makes it goes quicker, slower, stop or move, or changes its shape. Push or a pull measured in newtons. Okay, that's the most important thing about forces. Now, let me just get rid of that and we can move on. So sometimes in the exam, they throw up this idea of contact and non-contact forces. So what do you think the difference is? It's really not too tricky, is it? For a contact force, you've got to be touching it. To push something, you have to put your hands on it and make it go. However, gravity works if you're touching something or not. It doesn't, if you jump out of an aeroplane with a parachute on, gravity doesn't, nothing needs to get hold of you. You're in the middle of air, gravity is still going to pull you downwards. So it doesn't require a touch. So here are contact forces. So air resistance, you've got to actually touch air to get air resistance. Friction, where two things rub together. Buoyancy, where something is being floated upwards. Drag, being pushed back. All of those things require something to touch them to be able to exert the force on them. Okay, so contact or non-contact. So friction, where would we put friction? Would we put it in contact or non-contact? So yet again, I'm afraid I've got a poll for this one. I hope I have. Fantastic. So what do we think for friction? Is it a contact or non-contact force? Can you have friction without contact? Absolutely fantastic. Straight in there with the right answer. It's a contact force. Okay, you can't possibly have friction without contact. And there are some other ones here. Now, I don't have polls for these ones because this is your task to just cut and paste those under the right heading. So there we go. Okay, so you have a little look about where you think those go. Try doing it before you look at the next slide that I'm going to go past really quickly. Okay, oh no, I haven't got it. Good, I've taken it out. I had the answers on there. Now, I'm going to skip through this one. No, I'm not. When two objects interact with each other, they exert equal and opposite forces. You will have all tried this. If you tried to stand on a skateboard and push on a wall, as you push on the wall, the skateboard goes in the other direction. If you've ever been on a school camp or a camp of another sort and you've tried to get out of a boat, as you push on the boat to go that way, the boat tries to go away from you. Same time, if you fire a rocket on fireworks night, you light it, the rocket pushes down, that pushes the rocket up in the air. It's something we've all seen all of the time. Okay, we're quite used to it. But one of the things that we don't think about is actually it's happening when things aren't moving. If there is a book sitting on a table, weight, gravity, is pulling the book down. Now, for the book to be held up, the table must be pushing backwards. Now, in your exam, they will ask you to do this thing here. I'm just going to go around, draw a free body diagram. What they mean by that is draw a diagram that has got arrows on it to show the forces. And remember, we said the size of the arrows really matters. So if you look down here, the weight of the book going down and the reaction of the table pushing it back up again, those arrows are the same size, and they must be the same size because the book isn't moving. If the book was being thrown upwards, let's say it had rocket thrusters under it, this arrow going up would be bigger than the arrow going down because it was moving upwards. The resultant force was up. If the book was falling to Earth, the arrow going down would be bigger because gravity or the weight would be pulling it downwards. It's not moving, they must be equal. Use a ruler in your exam. Free body diagram. Drawing those on. So there they are. So we could do a free body diagram for this one. There's a person sitting on a chair, okay? And they are not moving. So we would draw an arrow downwards, per person sitting on a horse. Now, weight and mass. Again, vector, scalar, units of force, velocity, Newton's third law. That's every action has an equal and opposite reaction. It's in red on the one before. Now, there's a bit of an equation on this one. Now, if you're doing the foundation paper, and you should be if you're in here, is you don't have to memorize this equation, but it's not a tricky one to remember. They're more likely to give you this. Okay, and remember, we've already said weight and mass are the same, are a different thing. Okay, so let's just move on, and because the answer is no. Weight is the force of gravity acting on that object. Weight is how hard it is being pulled down. It's got a direction. Weight is down onto the ground and it's due to gravity. Mass is how much of something you've got. Now, its weight on Earth gets bigger if its mass gets bigger, because the more of it there is, the harder gravity pulls it down. But mass is not a measure of how hard it's being pulled down, it's how much there is. If I had 20 kilograms of crunchy nut cornflakes, I don't know why that's come in my head, but I really like them. 20 big boxes. If I had 20 kilograms of crunchy nut cornflakes and I took them to the moon, I would still have 20 kilograms of crunchy nut cornflakes. There would be no less in any of my boxes, providing I hadn't eaten them on the way. But if I put them on scales, they would weigh less because gravity on the moon is smaller. So I've not been shortchanged. I've not got less crunchy nut cornflakes, but they weigh less because the moon pulls them less hard than the Earth. So this is how we work it out. Weight, which is measured in newtons. I know when we go in shops, we think it's in kilograms, but that's because people do things the wrong way around. It's not weight, it's mass that we ask for in the shop. Weight is mass times gravitational field strength, or gravity. Let's just call it gravity. Weight is mass times gravity, because if I go to the moon, gravity is less, so I have less weight, but my mass hasn't changed. And we can look at how we would work that out. So use the equation to find the weight of these things. So what I want you to do is to write the weight afterwards. Now it says here, gravity is 9.81. We can use gravity as 10, unless they tell you it's 10. So let's imagine it is 10, and let's see if we can do any of those questions. Why don't we try the second one? Because I think the second one is probably a little bit easier to do. So if we took gravity to be 10, and the equation was weight is mass times gravity, what would the answer to the second one be? Okay, what would the answer to the second one be? Weight is mass times gravity. So the mass is 70. Awesome. And straight in there, we've got 70 newtons. Now, I see absolutely what's happened here. So absolutely correctly converted it to newtons, but we've got to do 10 times 70. So the answer would be 700. Let's go back and look at our equation again, because I don't want people to get confused. Okay. So if we're asked to work out the weight, we multiply the mass by gravity. So the mass is 70, and I said let's use 10 for the gravity. So we've got 70 times 10, which gives us 700. I'd like you to try some of those on your own when your teachers post this in your classrooms. And you can take gravity. In fact, I'm going to change it on the slide to 10. We can take it as 10. Sometimes they give you a different number in your exam, but normally we can take it as 10 unless they do. And there are some other questions here. So if forces are balanced, stationary objects stay still. Remember our book. Our book had the same size arrow going up and down, which means that those forces are exactly the same. If an object is moving at a constant speed, okay, that means that its forces are also balanced. Okay, so they must be absolutely the same. So in here, stationary object, zero resultant force, stays stationary. Zero resultant force, moving object, keeps moving, same speed or same velocity. But if we had a non-zero, if we had a resultant force, that's what non-zero means. We have a resultant force. Stationary objects, remember all the way back at the beginning, we said, well, now they start to move. Because if we push an object, it moves. And in moving object, it either gets quicker or it slows down, depends which way your resultant force is. So you need to fill that in on this table, okay? And I won't say it again, you might have to rewind this little bit of video to make that make sense, okay? And then you have to calculate the resultant force. So how we work out resultant forces, remember, is that these are all opposites. So weight of the brick is 120, but these arrows are identical. So that means it's 120 up. So that's 0. We can ignore that. We've got 38 and 38 going that way. So we have to add, oh no, it's just the one. Friction force 38 and 38. So we've got 38 going that way. We've got 51 going that way. So we need to take 38 from 51 and find the number. And then we need to give it an arrow, a direction on there. So you need to calculate that. And there are some forces on here for you to try and name and say whether they're balanced or unbalanced. And that is everything that we are doing today. Just to recap, forces and resultant forces and vectors and scalars, ready for a quick quiz next week, end of next week. So I'm going to do another revision webinar next week on Wednesday, and then Thursday and Friday, there'll be a quiz for you to fill in, for you to test whether your revision techniques have worked. Remember, revision techniques that I've asked you to try are the retrieval techniques, where you write down what it is you're trying to remember, you cover it, give it a second, try and write it out again, look at what you've missed, and then come back to it again. Okay? That's the main one that I want you to practice here. So unless anyone's got any questions, that is the end.